Download this code from codegive.com, link in the description below. OK, let's dive into Ac251c unidad 0, focusing on byte alignment and byte ordering, endianness, within the context of the architecture, along with practical code examples. This is a foundational concept for understanding how data is stored and manipulated in low-level programming, especially on systems like Ac251c, which might have specific constraints or behaviors. Understanding byte alignment and byte ordering. These two concepts are crucial for writing correct and efficient code, especially when dealing with data structures, structs/classes. Interacting with hardware, example memory mapped I/O. Networking, transmitting data between systems. Porting code between different architectures. 1. Byte alignment. What it is. Byte alignment refers to the memory addresses at which data objects, variables, struct members, etc., are stored. The processor often has restrictions on the addresses it can efficiently access. For example, a 4-byte integer might need to be stored at an address that is a multiple of 4. Why it matters. Performance. Misaligned accesses can significantly slow down memory operations. Some architectures might require multiple memory cycles to fetch a misaligned word or even throw an exception, alignment fault. Correctness. Some architectures strictly require alignment. If you try to access a misaligned value, your program might crash or produce unpredictable results. Portability. Different architectures have different alignment requirements. Code that works on one architecture might fail on another due to alignment issues. How it works. Compilers often insert padding bytes into data structures to ensure that members are properly aligned. The default alignment for each data type typically matches its size, example a 4-byte integer is aligned to a 4-byte boundary. Common alignment rules. Char, typically aligned to a 1-byte boundary, any address is fine. Short, typically aligned to a 2-byte boundary, address divisible by 2. Int, typically aligned to a 4-byte boundary, address divisible by 4. Long, typically aligned to a 4-byte or 8-byte boundary, depending on the architecture. Long, typically aligned to an 8-byte boundary, address divisible by 8. Float, typically aligned to a 4-byte boundary. Double, typically aligned to an 8-byte boundary. Pointers, typically aligned to the size of the pointer, usually 4 or 8 bytes. Example, in C. In this example, you'll likely find that the compiler adds padding after A and C to ensure B and D are properly aligned. 2. Byte ordering, endianness. What it is. Byte ordering, or endianness, refers to the order in which bytes of a multi-byte data type, like an integer or floating point number, are stored in memory. There are two primary endianness schemes. Bigendian. The most significant byte, MSB, is stored at the lowest memory address. Think of it as the big end coming first. Little endian. The least significant byte, LSB, is stored at the lowest memory address. Think of the little end coming first. Why it matters. Data interpretation. If you read a multi-byte value from memory, you need to know the endianness to interpret the bytes correctly. Networking. Network protocols often specify a particular endianness, typically bigendian. When sending data between systems with different endianness, you might need to convert the data before sending or after receiving it. File formats. Some file formats are endian specific. Asterisk portability asterisk endianness is architecture dependent. Code that assumes a particular endianness will be non-portable. Asterisk example asterisk consider the integer value 0x123456778. Asterisk big endian asterisk memory would contain 12345678 MSB first. Asterisk little endian asterisk memory would contain 78563412 LSB first. Asterisk detecting endianness asterisk you can use a simple code snippet to determine the endianness of your system. This code checks the value of the first byte of an integer. If it's 1, the system is little endian, otherwise, it's big endian. Asterisk endian conversion asterisk. Asterisk you might need to convert between big endian and little endian for network communication or data storage. Standard libraries often provide functions for this. Asterisk HTNL, host to network long, convert host byte order to network byte order, typically big endian. Asterisk HTNS, host to network short. Asterisk NTAL, network to host long. Asterisk NTOS, network to host short. Asterisk if you don't have those available, you can implement your own conversion functions. Ac251c considerations, specific to unidad 0. Now, let's bring this to the context of Ac251c unidad 0. Because I don't have specific documentation for that exact processor and specific unidad, I'll need to make some informed assumptions based on typical embedded systems and the context of unidad 0, which likely means early initialization or hardware configuration. 1. Determine endianness asterisk. The first thing you need to establish is the endianness of the Ac251c. Consult the processor documentation. If you can't find it explicitly stated, try running a test like the endianness detection code above if you have a development environment set up. This is critical. 2. Alignment restrictions asterisk. Asterisk consult the processor manual for alignment requirements. Pay close attention to instructions that deal with memory access, load, store, etc. Are there specific alignment rules for int, short, long, and double types? Asterisk if you're writing interrupt handlers or directly accessing memory map peripherals, alignment is especially important. The hardware registers might be at specific addresses with strict alignment requirements. 3. Compiler/assembler behavior asterisk. Asterisk understand how your compiler handles alignment by default. Many compilers have options to control alignment, example pragma-pack, push, 1, in some C/C++ compilers to disable padding. However, be very careful when disabling padding, as it can lead to alignment faults or performance penalties if the architecture requires alignment. Use such options only when you have a good reason, example matching a specific data layout for a file format or communication protocol. Asterisk if you're writing assembly code, you're responsible for ensuring correct alignment. Assemblers often have directives, example .align for in some assemblers, to align the next data or instruction to a specified boundary. 4. Unidad 0 specifics asterisk since unidad 0 likely deals with early initialization. Asterisk bootloader/startup code asterisk pay attention to how the bootloader or startup code initializes memory regions. Ensure that data structures used in the startup process are correctly aligned. Asterisk memory mapping asterisk if you're setting up the memory map, defining the addresses of different memory regions, be aware of alignment requirements when placing data structures in specific locations. Asterisk interrupt vector table asterisk the interrupt vector table, which maps interrupt numbers to handler addresses, must be correctly aligned. Asterisk peripheral registers asterisk when initializing peripherals, access their configuration registers using the correct alignment. Code examples for Ac251c, with assumptions. Because I don't have the exact Ac251c documentation, I'll provide examples that are likely relevant, with strong warnings to verify the details with the processor's official documentation. Asterisk example 1, assuming little-endian and 4-byte integer alignment. Explanation and cautions asterisk. Asterisk volatile keyword asterisk. The volatile keyword is crucial when dealing with memory map peripherals. It tells the compiler that the value at that memory address can change unexpectedly, example by hardware, so the compiler should always read the value from memory and not optimize by caching it in a register. Asterisk address casting asterisk casting the integer address 0x40000000 to a pointer of type volatile struct peripheral config asterisk tells the compiler how to interpret the memory at that address. Asterisk little-endian assumption asterisk. The read_little_endian function assumes the architecture is little-endian. Asterisk if Ac251c is big-endian, this function will give you incorrect results. You would need to reverse the byte order asterisk. Asterisk alignment of peripheral config asterisk. Make sure the entire peripheral config structure is placed at an aligned address, usually a multiple of 4 or 8. If you're allocating it dynamically, use malloc or similar functions, which typically return aligned memory. Asterisk peripheral documentation is key asterisk. The most important thing is to have the documentation for the peripheral you are accessing. It will tell you asterisk the base address of the peripheral, asterisk the offsets and data types of the registers, asterisk any alignment requirements for the registers, asterisk the endianness of the data. Asterisk example 2, assembly code, illustrative, requires Ac251c instruction set. Explanation of assembly code asterisk. Asterisk this is a highly simplified and illustrative example. The actual instructions you use will depend on the Ac251c's instruction set architecture, ISA. Section.data asterisk defines the data section where variables are stored. The .word directive allocates 4 bytes for the integer. Section.text asterisk defines the text section where the program's instructions are stored. Law, load address loads the address of the my_int variable into a register. LW, load word loads the value stored at the address in R0 into register R1. Endianness handling the crucial part is determining whether you need to swap the bytes in R1 after loading. If Ac251c is little-endian, the bytes will be in reverse order in the register. Key takeaways and things to do 1. Get the documentation The single most important thing is to get the official documentation for the Ac251c processor and any peripherals you're working with. This will tell you the endianness, alignment requirements, memory map, and instruction set. 2. Experiment write small test programs to probe the architecture's behavior. Try misaligned accesses, if possible, to see what happens. Use a debugger to inspect memory and register values. 3. Use portable types use stint.h for portable integer types, example uint32_t, int8_t. This makes your code more readable and helps avoid size-related issues when porting. 4. Be explicit when dealing with endianness, don't make assumptions. Use conditional compilation or explicit conversion functions to handle different endianness scenarios. 5. Understand the tool chain learn how your compiler and assembler handle alignment and byte ordering. Read the compiler and assembler documentation. 6. Test thoroughly test your code on the actual target hardware to ensure it works correctly. By carefully considering byte alignment and byte ordering, and by consulting the Ac251c documentation, you can write correct, efficient, and portable code for this architecture. Remember to adapt these examples to the specific requirements of your Ac251c configuration. Good luck.